right? Good. Hello, welcome to episode 1 of the How to Build A series. I'm Josh, one of Castle Microwave's application engineers, and will be your host for this episode. I hope everyone in the back can hear me. In this series, we'll be going over the basics of CST Studio Suite and exploring the interface, the modelling, and some of the simple simulations to grasp the general utility of the software. If you are a beginner, just getting started, a seasoned pro looking to see if there's any new and interesting tips, or even just curious, welcome. If you are watching live, please feel free to drop any questions in the comments section, and either myself or Mark will look to answer these for you. If you are looking for a more in-depth answer or licensing for CST, please use the Google form, which should have been provided to you previously. This can also be found in the description below. For those that are hoping for something more complex, subscribe to the channel and check back regularly. We will be rolling out more complex and in-depth series as the weeks progress. Without further ado, let's begin. Part 1. Project Template. Application, Workflow, Solvers, Units, Frequencies, and Monitors. Today, we will be constructing a horn antenna and studying its gain performance. Horns are widely used as antennas at UHF and microwave frequencies. They are used as feed antennas for larger antenna structures such as reflector antennas, and as standard calibration antennas to measure the gain of other antennas. They offer moderate directivity, low VSWR, broad bandwidth, and simple construction and adjustment. To start, open CST Studio Suite and navigate to the new project template. This template we are creating will be useful for you to use in future for X-band antenna devices. When your pie chart pops up, select Microwaves and RF Optical. This will take you to a section which lists a few general categories to start from. As you can see, the other sections also have general categories, which are always a great platform to start from. In this instance, we're going to go back to Microwaves and RF Optical and select Antennas. Click Next. As we're building a waveguide horn, we'll select Waveguide, in brackets, horn, cone, etc. and click Next again. Here we have reached a key section. Which solver will we be using to compute our simulation? Each solver has its benefits depending on the sort of model you are designing and the measurements being taken. To not overload at the beginning, we'll only cover time domain in this video, as this is the one we are using. Time domain solver itself can be broken down into two methods of solving the Maxwell equations. We will be using the finite integration technique, just called transient solver. The time domain solver calculates the development of fields through time at discrete locations and at discrete time samples. It calculates the transmissions of energy between various ports or other excitation sources and/or open space of the investigated structure. Consequently, a time domain solver is remarkably efficient for most high-frequency applications such as connectors, transmission lines, filters, antennas, etc., and contain the entire broadband frequency behaviour of the simulated device from a single calculation run. The time domain solver, or transient solver in this instance, calculates the fields step by step through time by the leapfrog updating scheme. It is proven that this method remains stable if the step width of the integration does not overcome a known limit. This value of the maximum usable time step is directly related to the minimum mesh step width used in the discretization of the structure. Therefore, the denser the chosen grid, the smaller the usable time step width. This means that a high mesh resolution of a small detail inside a given structure possibly determines the global time step and therefore the total simulation time. However, the transient solver applies some highly advanced numerical techniques like the Perfect Boundary Approximation in combination with the thin sheet technique to allow accurate modelling of small and curved structures without the need for an extreme refinement of the mesh at these locations. This allows for a very memory efficient computation together with robust hexahedral meshing to successfully simulate extremely complex structures. In addition, features like AR filtering or S-parameter symmetries and reciprocity help to increase the performance of the solver. Furthermore, the simulation becomes even more efficient when applying hardware acceleration like GPU or MPI computing. Enough of that. Select time domain and click Next. For our units, we'll be using inches, gigahertz and nanoseconds. For now, let's not worry about these other units. They are important in some calculations and design, but in our case, we won't need to worry. Select Next again. As we're in the X-band, let's define our minimum and maximum to match that, 8 and 12 gigahertz. And let's monitor the electric field, the magnetic field, and the Farfield pattern in the simulation. As we're designing this antenna for 10 gigahertz, let's define it for that frequency. As we've set the bandwidth, it has automatically filled this in, but we're only worried about 10, so let's remove the other two for now. So it just reads 10 gigahertz. Select Next. Is this summary of everything we have set up? And let's give it a suitable name, so something we can find later to reuse again. Let's use X-band horn and click Finish. Step 2. Modelling. Bricks, cylinders, parameters, picks, the working coordinate system, Boolean, and shape tools. We're now introduced with the core interface for high frequency modelling. Depending on your personal setup, you'll have the following. A navigation tree on the left, excuse me, I've got headphones covering it. A navigation tree on the left, messages and progress in the small half space on the bottom right, and parameters and result navigator in the small half space in the bottom left. You can also move these about freely to your preference. So I could bring it out here, I could pop it in here, and I can put it back. If, for example, I was to close this off and you needed to view it again, you can reopen it by right-clicking one of these spaces here and ticking the object. And there we are, parameter list is now back available again. Before we build, I'll quickly cover navigation options. On the View tab at the top, you'll find the mouse control category. I personally have this set to pan, but please feel free to have a go at using each one to see which suits your needs. If I have it set to pan, I can then use Control to rotate around and Shift to rotate in the plane. You can also use spacebar to restore fit to view, and 0 through 9 provide some default alternative views. We use 0 to go back to standard isometric and space to fit. Let's return to the Modelling tab. We'll start with picking our 0 reference point and setting a local working coordinate system. Just a quick side note, picks are your best friend with modelling in CST, and I encourage exploring what each of them does. They are found here in Modelling tab, where you can have pick points and picks, as well as pick lists. For this instance, we're going to use pick from coordinates, and we'll select 0, 0, and 0 as our pick point. Now this is displayed as a red dot on the screen. We'll set as our local working coordinate system by clicking this or using the key W. Now select brick in the shapes category. If you are to now double click anywhere in the free space and then move around, you can see a 2D shape forming. If you are to double click again, you will lock in these two axes, and then you can drag in a third to make this an initial cuboid. Now you've done that, select OK to confirm it. But what we're going to do is actually go and backtrack and delete it. If you look in the Modelling tab, in the Edit category, there is an option called History List. Open that and you'll see all of the operations that you have performed so far. It's ideal to be efficient with your actions and only keep the steps you need to build your design. Select the Define Brick step and delete it. You can also hide steps, which keeps it available if you want to come back to it, and this allows it to be available but not running in the current modelling process. If you press Update now to complete the action, you will notice we're back again where we declared our local working coordinate system. Select brick again, but now press Escape, and you can see that we can define all the dimensions of the brick at once. We'll put the following as our dimensions: x min, x max, y min, oh excuse me, rather, it shouldn't be that at all. It should be, we'll use our x min, or rather our u min, as minus 0.5, our x max, or u max in this case, as 0.5, our v min as minus 0.25, and our v max as 0.25. We'll use z min as 0, and finally z max can be 0.5. If we press preview, we can see, and then press the spacebar again in the free space to see, a rather rudimentary and initial brick is formed. That is 1 inch by half inch by half inch, with the height and width centered on our working coordinate system. If we are happy that this is the dimensions that will be used, and we did not want to be able to easily change them, we could select OK, after changing the name to something suitable and choosing the correct material. But because we're CAD, so CAE engineers, we want to be able to change the dimensions rapidly, and that's where parameters become very important. Let's edit our dimensions. Let's change the u min and max to be guide w divided by 2. So minus guide underscore w divided by 2, and guide underscore w divided by 2. Just give me 1 second, I've just been noted that the microphone's a little bit quiet. If this is too loud at any point, please let me know in the comments. Hopefully this should be a little bit easier for you to hear me. As we were, we'll use minus guide, oh, we've got 2 there, minus guide underscore v divided by 2, and guide underscore v divided by 2. V min can be 0, and V max will have as guide underscore D. If we were to click preview now, we are asked to define the parameters for these. Remember, our width was 1 inch, so we can use 1 here. Our height was ½ inch, so we can use 0.5 here. And our depth was also ½ inch, so 0.5 again. Now you'll see if you click preview, nothing actually changes because what we have defined here is exactly the same as what we had previously, but now as parameters. Let's make sure our material is a perfect electrical conductor, and we'll give a name for our brick, and we'll call it guide. Press OK, or select enter. And now we have our fundamental brick that we can now work from. If If you were to look in the bottom, you could see the list of parameters we have just defined, such as guide V, guide D, and guide W. If we were to change one of these, such as the guide W, which is the depth of our object in the W plane, we could change that to 4, and then if we use F7, it will update. Sorry, guide W is the width of the object, depth is D. Technically this should probably be guide U rather than V, but we'll leave it as that for now. If we change this back to 1, it resets back to how we want it, and we can carry on. Now open the Picks menu and select Pick Face. And we select the front face here, and we will set this as our local working coordinate system, W key. Let's transform the working coordinate system away from the guide by 2 inches. So if we select Transform Working Coordinate System, and we can then transform this in, and if you wanted to make sure which way you were going, you can see how these change here from where it's. So we want to move 2 inches away, so it's the DW we want to change. Now we could just type in 2, but when parameters are your best friend and we want to be able to modify this quickly, we'll give this a name and we'll define it as horn underscore L. Preview again, and I'll set that to 2 inches. Okay. Now select cylinder from the shapes menu. Cylinder is found here, and again we'll just use escape to define all of the parameters at once. We'll use horn R for the outer radius, and horn D for W max. Everything else can be 0. If we select preview again, we'll set horn R to 1 to have a radius of 1 inch, and horn D, which will be the depth of the object, to 0.25. Select OK. If you click in the free space and press space, you can fit everything in. And you'll see here we're going to be producing a cylinder in this space. We'll name it horn and select OK. Now once again we'll pick the front face of this section we've named guide. We go to pick points, or rather sorry, picks and face. You could also use the F key. Select this and then spin round depending on how you have your mouse controls. I'll hold control and spin round, and then use F key again and select the back face of the cylinder. We're going to be connecting these together, so in the shapes category, which is here, select loft. It looks like these two, should we call them grey or silver circles connected by 2 red lines, and we'll loft. We'll make sure minimize twist is selected, we'll keep smoothness low, and if we click preview to check the builders correctly, we can see that they will be connected together, and select OK. We won't worry about naming this object, and we'll see why shortly. Now, if you move around again, you can see that it's finally starting to look like a horn antenna. 0 to isometric, space to fit. But now we need to make it a single object. So in the Components tab found in the Navigation tree, select the drop down here into Component 1, select the horn, and click Boolean. You can see here there are various Boolean options, but we're going to be using a Boolean addition to join all the objects as one. Select this, then whilst holding control, select guide, select guide, then holding control, select solid 1. Press enter or return to confirm this command, and everything will now be a single object named horn, as all the objects are connected together and the name comes from the first item selected in the way we performed the Boolean operation. Now, with the F key to pick face, remember you could always go up here, the F key is quicker. We'll select the front face of our now horn, pivot round to the back and select the back face of what was the guide. In the tools section, we'll find shape tools, which is here, shape tools, and select shell solid or thicken sheet. Remember, we'll use a parameter for this thickness, so we'll use horn underscore T, and we'll select outside to maintain the outside surface and cut away the inside. Use preview to be able to set the parameter, and we'll set that as 0.01 inches. OK to confirm. You can see what is about to happen. OK to confirm this as well. Congratulations, you have just modelled a waveguide horn antenna. This now ends stage 2, and we will now begin stage 3, the simulation setup. Step 3, simulation and results. Boundaries, symmetry planes, excitations, meshing, Farfield cuts, and solver settings. In order to test the performance of our horn, we need to give it an excitation. For this, we'll use a waveguide port. So we'll pan around to the back. I use scroll to zoom in because of how my view and mouse controls are. And we'll pick a corner of the inside of our guide. So I'll use P, but you can also go and use pick points and the picks menu. P is the quick command. I highly recommend familiarising yourself with all the commands, as it will make your modelling experience far easier, and you'll definitely enjoy using CST a lot more if you don't have to constantly walk and click. So double click this point, scroll back out, and now we'll select a non-adjacent edge to fill the space. So we'll select this one here. I'm just panning it around to make sure I do select this edge rather than this edge. So use E for eggs or echo, that's using the phonetic alphabet, and we'll double click this edge here. Now if I just zoom out, you can see it's a little bit hard. Excuse me. Did I change my... Apologies, I think I might have put my point there. Right, see? As a demonstration, I've somehow accidentally changed my local working coordinate system here. That must have been when I pressed W instead of E on the keyboard. If you now go to the history list, and you can see here, a line WCS is where we just expected it to be. So what we'll do is we'll go to this. To confirm that is what I've done, I will click Hide and Update, and you see that is now gone, and the working coordinate system is back where it should be, where we left it. It is always good to keep an eye on these things because it is very easy to make a mistake if you're rushing through, and just always double check what you're doing. So we're now happy with that there, so we'll leave it hidden for now, but what you could also do is delete it, but we'll leave it hidden because it's not going to affect. So now you have a picked point on the inside corner and the inside edge here. If we go to Simulation and then select Waveguide Port, and it will automatically fill the area around these picks. Select OK. This red box is now our waveguide port. In order to calculate the far field, we need to make sure the boundary conditions are set to open add space, and to reduce the calculation time we can employ symmetry planes. So if we go to boundaries, make sure they are all set to open add space, and then symmetry planes. For YZ plane, we can use magnetic HT equals 0, and the electric plane can be symmetrical in the XZ plane, so electric here. So now we've reduced our calculation time to a quarter because we will only be simulating this area because it's geometrically symmetrical. It's a bit of a tongue twister, there we go, around these axes. Select OK. now, if you go into Mesh View, you can scroll in and see where the thin sheet technology would be employed in these squares of meshing, where we have empty space followed by our metal perfect electrical conductor followed by more empty space. We'll go to the Farfield cuts, so select Farfield and go down to Farfield cuts, and we're going to remove the theta 90, as we're not interested in this given we are building a directive horn. So just select delete. OK to close, and now go into Farfield result and select, sorry, it's on the wrong screen, here we are, and select max gain at selected frequency, which is this one here. Change the step size to 1 degree for the angular resolution of the Farfield, and now if we select browse monitors, again on the wrong screen, and choose Farfield F10 and OK. OK and confirm all. Close again. Now let's open the solver setup and make sure our accuracy here, so in simulation, let's just zoom out for you, hang on, there we are, and 0. Set up solver and make sure our accuracy is minus 40 dB, which is where the steady state conditions have been achieved and the computational domain threshold is set. Start the setup. You can now see the solver running, and our setup prevents us from making any main changes from the model until the computation is complete. Now the calculations are complete, as you see here, we can view the results. If we check the energy folder in 1D results, we can see that the energy decay is quick because of the lack of resonant behaviour. Checking the port signals, we can also see how much of the signal is reflected. To find out our return loss, let's check the S parameters, which is here, and we can see that the antenna exhibits wideband behaviour with minus 15 dB over the full range of defined frequencies. From the power excitation, we see that most of the power is radiated away. And if we check out our, no, not that one, port modes, lost it now, as always. If we check our port modes, we see the fundamental mode is indeed TE10, and the cutoff frequency is listed as just short of 5.9 GHz. To view our E-field plots, let's select fields on plane and normal X-plane. So we go to E-field, now my resolution is quite high, I'll probably need to turn this down for you just quickly. With default, let's have a quick look. I'll turn this down, maybe not that much. I say it was too small now. Bear with me just a moment, I'd like to make this look a little bit. Okay, right, we'll reduce the density and we'll just make these bigger. Okay. Fields on the plane. And we'll normal our X-plane here. Turn this sideways for you. You could also use key 1. And you can also animate these fields. feel free to also change these from arrows to contour, for example. And the contour plot of the Y component illustrates the radiation. Now let's check our Farfield. So we'll stop animating. We'll go down to Farfields in our navigation. We'll select Farfield 10. And we'll make sure Show Structure is enabled. Decrease the size a bit, or increase it rather, that's better. And we can see the antenna radiation in a 3D space. The two phi angle cuts we defined can now also be viewed. So here's phi 0 and phi 90. If we go into plot properties and table afterwards. So what you would do is go into Farfield, select the phi 0. I won't do this again because I've done it. Copy 1D results and OK. Then into the next one, properties, copy 1D results and OK. And then if you go back to 1D results, scroll down to the Farfield category, E field, and you can now see them overlaid on top of each other. Step 4. Optimization and post-processing. Boundaries, symmetry planes, excitations, meshing, Farfield cuts, and solver settings. In order to optimize our antenna for our purpose, we can now perform a parameter sweep on each of the parameters we deem key to the performance characteristics of the antenna. In this case, we will change the aperture size of the horn. Open the parameter sweep window, which if under home is here as par sweep. Select new sequence for our parameter. As we have already defined these, we do not need to go back and change it. We can select new parameter and horn R. We will use 3 samples and we'll go between 1 and 1.5 and select OK. Now we'll quickly start this and it will we'll delete our results and scan again. And if we look at our result navigator, when all of our results come in, we can compare them against each other. Oh look, okay, just finished in time. We'll go to our S parameter, and if we highlight, hold shift and highlight all our runs, we can see the result of increasing the aperture. We also go to our Farfield. You can now see here the difference. If we hide the structure as well, see the difference in our Farfield cuts by changing the aperture size. Legend on the right to demonstrate each. Now we need to check our max gain at selected frequency, which can be found in tables, 0D results, and at the bottom. And as expected from antenna theory, gain is directly proportional to the antenna aperture. Now let's do some Farfield post-processing. So we need a broadband Farfield monitor. Go to home, no, modelling, no, simulation, yes. Select field monitor. We'll select Farfield RCS. Make sure transient broadband is enabled. 21 samples would be fine. And select OK. Now if we select our horn parameter, wherever it may be, back to 1, we'll delete our current results, F7 to update the structure, and start simulation again. Collapse some of these for now. When the computation is complete, we will be going into the Farfield tab, and Farfield broadband should appear. Just unfortunately a waiting game. Modelling is actually the very quick part when it comes to CST. Modelling is done, and then simulation is what takes up a lot of your time. For this reason, it's always good to have the recommended hardware to run everything you could possibly need. As we're using the time domain, GPU and MPI acceleration would be ideal. Excellent, these have all just opened up, so let's collapse them again. We go into Farfield broadband. We'll go back to 3D. We'll show structure again. Just decrease the size to put it inside, about there. If we go to the properties, Farfield plot, we can animate by pressing start. It's just running the computation for each. And there you are. You can now see the animation at 10 GHz. Any frequency inside the frequency range can be plotted. Interpolation is performed between the anchor frequencies. Now let's extract the maximum gain versus frequency. So we'll close this, we'll leave it to run, as long as your computer can support it, there's no reason not to. We'll go to Farfield result, pan this over the top, and we're looking for max gain over frequency. Okay, that's actually getting a bit annoying, let's stop that. I regret that decision. Properties, stop. Farfield result, max gain over frequency, and OK. Select it in this one, and then press evaluate, and this will now evaluate the template. Now this is done, our results immediately pop up. We'll close this. We can see that our max gain over every frequency band is detailed here. We'll now go into co and cross polarization. The co-polarized Farfield component has the same polarization as the excitation, the y-oriented in our case. The cross-polarized Farfield component is orthogonal to the co-polarized component and main lobe direction. In order to use different polarizations for transmitting and receiving data simultaneously using the same propagation channel and the same frequency, an antenna design goal might be to maximize the co-polarized and minimize the cross-polarized component. If we go back to our Farfield, the linear directional icon plots the co-cross-polarized components using the Ludwig III system. So if we expand it, we can look at the Ludwig III cross-polar and the Ludwig III copolar. That one. So there's our cross-polar and there's our copolar. In antenna design theory, the phase center is the point from which the electromagnetic radiation spreads spherically outwards, with the phase of the signal being equal at any point on the sphere. For a directional antenna, equiphasic behavior is required around the far-field main lobe in order to send clean data. When designing reflector antennas, which we might cover later on, the best position of the horn antenna to get the best radiation performance is to match the focal point of the dish with the phase center of the horn. So if we were to work out the phase center calculation, if we were to highlight the copolar phase, go to properties, look at the phase center, select calculate phase center for ball site, for the H plane, we want our angle to be half the high power bandwidth, and show phase center and apply. We OK this. It's hard to see here. Hang on, let me just, if I decrease this to make it easier to see, you can see here the phase center is calculated and it is also provided in the detailed description box down below. To check the phase center correctness, we can go into Farfield plot, because by default the origin is used as reference for the Farfield plot, including the phase calculation center of the calculation. So if we go to set this to Cartesian, oh, it's gone away. Farfield plot. Why is it playing to the buttons again? Okay. Oh, copolar. That's why I had our phase. Cartesian. If we go back to our properties, origin, make sure center on bounding box is ticked, and OK. Now how to check the center coordinates are the correct ones. If we set as origin of Farfield previously calculated coordinates to the phase center. So if we go back to properties, origin, free, and we had that as 2.76, and OK, or apply, and OK. The scaling is completely out on this, but really we're looking between this region here, and we can see that the phase is now constant over the Farfield lobe H plane. It's got a little bit rocky at the end, I must admit, because some of the scaling was out. If you need to do this yourself, highlight the area you wish to view and it will snap to view. This can be seen in the Farfield pattern if we go back to 3D. This region here in 2D, undo, polar, here, this 20 degrees region. This now concludes the very initial video of modelling a waveguide or horn antenna. This is only a quick overview on modelling. The results were just a brief snapshot into some of the utility. If you're looking for in-depth results modelling or results post-processing and other simulation events, keep tuned and subscribe to the channel, and we'll be able to explore these for you at a later date. Thank you for watching. Don't forget to always drop questions in the comments, use our forms, and if in doubt, get in touch at sales@castlemicrowave.co.uk. No, sorry, at castlemicrowave.com. Or phone 01635 271 300. I've been your host, Josh Wilson. This has been a horn antenna.